Be a party pooper, learn about party poppers. So party poppers, those like champagne poppers, the old school ones, they actually have like a little bit of gunpowder inside of them. What happens when you pull that string is you're creating friction. This friction is providing energy that is going to kickstart an oxidation reaction we'll talk about. What you need to know is that this reaction is really energetically favorable. This means that it's spontaneous, but it doesn't just like happen all of a sudden. You have to put that little activation energy in. This is what you do when you pull the string. What we mean by spontaneous is that this reaction is going to be exergonic. It's going to let off energy, and that energy is going to be used to shoot confetti through the air. And the champagne shape isn't just so that you can say, oh, it's like New Year's champagne. It's that it's like the shape of the container is going to help like focus that energy away from your face and shoot the confetti out. When you see the confetti shoot out, you can see that it's kind of like all loosey-goosey all over the place. This is like what's happening inside with the molecules. They're getting all loosey-goosey all over the place. You're increasing the entropy, the freedomness, the disorder of these molecules. And this is going to be one of the ways that you can get a reaction to be exergonic, to be energetically favorable, to let off energy. The other way is by, so we call that entropy, the like randomness or disorder. There's also enthalpy. This is basically when molecules trade in like uncomfy high energy bonds for more comfy weaker bonds or stronger bonds. And these bonds, the molecules can kind of relax, and if they're relaxing, then they can kind of release all that pent up energy. So when we have reactions that have an enthalpic benefit, that is also going to contribute to the overall energy release. In the reaction we're talking about in these party poppers, I'll get into it more in detail, but this reaction is going to be both enthalpically favorable and it's going to be entropically favorable. So basically, it's going to trade in weak, like oxygen-oxygen bonds. You're going to undergo this oxidation reaction, split those oxygens up from one another, and then put them onto other molecules. And this is going to create those lower energy bonds that are going to then the higher energy, like the difference between those energies is going to be given off and help contribute to the confetti popping out. And so this is an oxidation reaction. So we'll talk more about oxidation and reduction in a minute. So that was the enthalpy side of things. So basically, you're going to trade those weaker bonds that are uncomfy for stronger bonds that are more comfy. Now what you're going to do is you're also going to have the entropic benefit. You're increasing the randomness or disorder. When you undergo this reaction, you're going from solid components to solid and gas. And in a gas, the molecules have more freedom to move around. And when they have more freedom, they have more entropy, they're happier, they've let off energy. And so you get this entropic benefit. And you can actually see this entropic benefit when you look at all that confetti kind of like shooting out and uncoiling and stuff like this. You can imagine the molecules themselves in like the gas, you're creating more of these molecules and they're going to have more ways to move around because they're not tied to, like, they're not stuck onto one another like they would be inside of a solid. So that's your entropy benefit. And then you have the enthalpy benefit from the bonds. Put those together combined with the fact that the entropic benefit is going to be amplified at a higher temperature. So you can kind of think about like if you are hotter, you're going to want to spread out more, right? Similarly, if molecules are hotter, they're going to want to spread out more. And so the entropy is going to be more important. When you're doing this reaction, you're letting off heat. This is where like the enthalpy, you can also think of it as like heat. And so if you have a molecule that is a reaction that's enthalpically favorable, it's going to be letting off heat. Since you're letting off heat, you're going to be then amplifying the effects of the entropy. So overall, you get this really exergonic reaction, this reaction that's going to let off a lot of energy. And then the trick of the party popper is just to funnel that energy out away to shoot the confetti out. So it's a really, really cool like demonstration of the principles of thermodynamics, and it's also a great way to talk about redox or reduction and oxidation. So let's step back and let's talk about that reaction that's going on, because this is the reaction that's going to be driving this. We're going to see that because this reaction is energetically favorable, it's going to actually provide the activation energy that's needed to get it started. So just because something's energetically favorable doesn't mean that it's just going to randomly happen. Just like if a couch across the room is more comfy, it doesn't necessarily mean, and you'd be happier in it, you could squirm less, you'd be able to spread out more. It doesn't mean that you're actually going to just like randomly, you're just going to like spontaneously end up on that couch. You have to get up and go and walk around across the room and sit down on that couch. Similarly, you might feel way better after you've completed your homework assignment, but you have to actually like put in the energy and do the assignment. So in this reaction, we're going to have to put in a little energy. This energy is going to break up phosphorus into a more reactive form, and it's going to help release some of that oxygen from its bound up form into a free form that can then, you have those weak oxygen bonds that can break and provide that enthalpic benefit. And so you need that activation energy in order to get this reaction going. Whenever you're breaking bonds, you're going to have to put in a little energy. But thankfully, we just need a little bit of energy. Just the friction of the pulling the string is going to provide enough energy in order to kickstart this reaction. And then this reaction, because it gives off so much energy, it's going to be able to keep driving that reaction going and going and going until it runs out of the fuel. So now let's actually talk about this reaction in a little more detail.
So the reaction that we're going to see is basically we're going to have potassium chlorate and antimony trisulfide and phosphorus, and these are going to all be in their solid form. The potassium chlorate is going to act as what we call an oxidant. I'll talk more about this in a minute. And then the antimony trisulfide and phosphorus will act as reductants. These are going to act as our fuel. Our final products are going to be potassium chloride. So this was chlorate, this was chloride. This is going to be the reduced form. You see it's lost the oxygen. And then we're going to get phosphorus oxide and antimony oxide. So these have gained the bonds to oxygen. And then we also get this sulfur dioxide. So again, something that has gained bonds to oxygen, and this is going to be a gas. Remember, gas, that's where we're going to get a big entropy gain. You can also see that we're getting a lot more molecules than we put in. And when you get more molecules than you put in, that's also going to be an entropy gain. So in order, though, to understand where the enthalpy gains are coming from, we're going to need to discuss this reaction in more detail. So this is an example of a combustion reaction. We've seen other combustion reactions when we were talking about candle burning and coal burning. What all of these have in common is that they're redox reactions. So we'll talk more about redox in a second, reduction and oxidation. And basically, these are redox reactions that are going to have a molecule that is going to react with oxygen. And it's going to then be highly exothermic. So it's going to let off energy. Often this is going to be given off as like fire and like heat and light and stuff, but not necessarily. And in fact, in our bodies, we actually have a slow form of combustion happening. We have oxidation reactions that are critical to metabolism, so the making and breaking of molecules. When we want to break down molecules, we do it through combustion reactions, where we're basically going to be doing a series of reduction reactions, where we're going to be removing electrons in a controlled manner, and then using them to like harnessing the energy from these reactions in a series of transfers in this thing called the electron transfer chain, the electron transport chain that's going to then use the energy from those different redox reactions, cache them in to store them in this form of ATP, and much more on that in my other posts. Because I'm normally focused on more biochemistry things, but the basic principles are the same, that in all of these cases, we're dealing with redox reactions. It's just that in our bodies, when we do it in this really controlled manner. Whereas when we're doing it when we're burning a candle or burning coal or letting off these party poppers, we're doing it kind of like all at once. So we're releasing that energy all at once. Let me just also note that the whole like definition of combustion is um, kind of loose. So often you're dealing with reactions that are going to be reacting like directly with oxygen. Other times you're going to be having reactions in which the oxygen isn't acting as like a gas, isn't reacting in its gas form, but it's coming from somewhere else. Is basically and then often it's all given off at once, but then it's not, as we see in the biochemical reactions. But in our body, we're typically just referring these as oxidation reactions. Whereas when we're doing it in one of these other forms, we're typically calling it a combustion reaction. But in all of these cases, they're oxidation reactions, or I should better say oxidation and reduction reactions, because they go hand in hand. So now that I've kind of skirted around the issue this whole time, let's actually go in, dive in, and talk about what oxidation and reduction really mean. It doesn't have to do, like, oxidation does not mean the gain of a bond to oxygen. It just happens to, like, often involve the gain of a bond to oxygen. What oxidation really means is the loss of electrons or electron density. I'll explain what this means in a second. And then reduction is the gain of electrons or electron density, because if something loses electrons, something else has to gain electrons. The oxidant is going to be oxidizing something else. So it's going to be gaining electrons because it's taking electrons from something else. That something else is getting oxidized, and the oxidant is going to get reduced. The reductant is something that is actually going to give the electrons to the oxidant, and in the process it's going to get oxidized. So you can see that they go hand in hand. And in the case of our chemistry popper, we're going to have our oxidant be the potassium chlorate, and then the reductants are going to be the antimony trisulfide and phosphorus. And this potassium chlorate is actually going to decompose or break down when we add the energy through that friction. It's going to decompose and release gaseous oxygen that can actually then react and form as the oxidant. So this isn't going to happen all at once. It's going to happen in a series of steps that we are going to set off when we pull that string. And so what are these electrons that I've been talking about? I talk about electrons a lot because they're involved in basically how atoms interact with one another, how molecules interact with one another, how atoms form molecules. So basically, each of these different elements are like carbon, nitrogen, oxygen, or in the case of these party poppers, we're talking about more obscure things when we're dealing with like antimony and stuff like this. These are all basic elements, and these are all elements that are made up of atoms. And so atoms are they're basic units, and they're made up of even smaller parts. So they have protons, neutrons, and electrons. The protons are positively charged, and they hang out with these neutral neutrons in this dense central core called the nucleus. And then they have this cloud of negatively charged electrons hanging out around them. Now, these electrons are going to be kind of like the most mobile and reactive parts of these atoms. And for reasons outside the scope of this post, different atoms have different like ideal numbers of electrons that they want to have. So they're always going to have a set number of protons, but they can actually give and share and take electrons in order to get to their kind of like ideal numbers of electrons. Especially in the case where you have metals, they have these like giant like electron clouds where they can kind of give and take different numbers of electrons and exist in various like oxidation states where they have different numbers of electrons. And this is going to make them really good for these redox reactions, because remember, redox is going to be the gain and the loss of electrons. So sometimes what we're going to see is actual like whole electrons being transferred, but other times what we're seeing is really just like a shift in the electrons. So you can think about the gain of electron density as being reduction, and the gain of loss of electron density as being oxidation. And what I mean by electron density is that when these atoms are basically when they share pairs of electrons in order to try to get to their ideal number. This is how they form molecules. So when atoms share pairs of electrons, they form what we call covalent bonds. But those electrons in the bonds are not always shared fairly. And so I like to think of these like atoms as kind of like the protons as being dog walkers. You have this positive pulling proton, that's protons that are going to be trying to rein in these electronegative or these electrons. So these like energetic dogs you can think about, especially the electrons in like the outermost electrons. We call these the valence electrons. They're going to be the most reactive. They're going to be pulling tight on that leash. They're going to be like trying to pull away from this leash, and the protons are going to be trying to rein them in. And how well they can rein them in is going to depend on the different atoms. So some of the atoms are what we call highly electronegative. This means that they have a really tight pull over that leash. And a great example of this is oxygen. So when something forms a bond to oxygen, oxygen doesn't just pull tightly on the electrons it started with, it also pulls tightly on the electrons that it was sharing. And so you get this like unfair sharing. This thing called like polarity. This can lead to like polarity where you have partial separations of charge even in a neutral molecule. And this, for example, is what makes water so sticky, is that the oxygen is going to be pulling electrons away from the hydrogens, making the oxygen partly negative and those hydrogens partly positive. And so you can see that the electrons, because what's happening when they share these pairs of electrons is they're kind of merging their electron clouds, like parts of their clouds. And so these electrons, there are places where they're more likely to hang out, but they're really moving around randomly. But if one of the atoms is more electronegative, they're going to tend to be clustered there more often. So we'd be more likely to find an electron hanging out around the oxygen than around the hydrogen. Now, what this means is that if you were to form a bond to an oxygen, you're going to be losing electron density because the oxygen is going to be pulling it away. And therefore, when oxidation is often, but not always, associated with the bonding to oxygen. And so when you see a bond to oxygen, that is going to be an oxidation reaction, typically because oxygen is one of the most electronegative atoms. And so basically anything that binds to it is going to be oxidized, mostly. And then what happens on the other end is hydrogen is not very electronegative. And so if you form a bond to hydrogen, it just has a single proton trying to pull in the electron. So it's not going to have a very tight pull, and it's going to not give you. It's going to therefore, you're kind of going to get to take its electrons. And so a bond to a hydrogen is often a reduction reaction. And so this is going to, this comes into play a lot when we're dealing with biochemical oxidation reactions. In our party poppers, we're actually going to see bonds to oxygen. So it's going to be easier to view this oxidation reaction actually happening. Okay. So when we see this reaction happening, what is actually going on? So what's actually going on is a couple different things. As I mentioned, this is going to be a very, very energetically favorable reaction, but we're going to have to put in a little energy to get it going. So when we say that it's energetically favorable, we're basically saying that the products have less energy than the reactants. So if things has a high energy, it's kind of like less stable, it's less happy. When molecules become more happy, they let off energy, they become like more stable. So you can think of how you're not very happy if you're like all anxious and you're kind of like swarming around. Molecules are like that too. When they're in a high energy state, they're going to be less happy. And then when they're more happy, they're in like a lower energy state, they can kind of relax that. And because energy can't be just like disappear, that energy is going to get released. And when you have the release of an energy, we call the reaction exergonic. And we represent this difference in energy between the beginning and the end as this delta G, where delta is talking about change in, and this G refers to this like Gibbs free energy. But this is going to be what we call a state function. So basically, it's just looking at the beginning things and the end things and not looking at the intermediates. So if we compare our reactants and our products, this is going to have lower energy than the reactants. So the reactants are going to be higher energy than the products. But this is overall going to be exergonic. But that doesn't mean that it's all like that there's not going to be endergonic steps, that steps that require energy. And in fact, we're going to have to put in energy in order to get over this like kind of hurdle. We have to have some activation energy to get us over the hump. So just like if you go on a roller coaster, there's going to be like, you have to go up the mountain in order to get to have that state where you go down the mountain. Something similar is going to happen in these reactions. And the higher the activation energy, the harder it is to actually get things going. In our bodies, we rely on using molecules called enzymes to try to like lower that activation barrier. And so these are often proteins, typically proteins, sometimes protein RNA complexes, sometimes just RNA. But basically, they can hold things in a position that makes it more favorable to react and things like this, lower the activation barrier. In the case of our party popper, we don't have proteins helping us out here, but instead we're going to directly add the energy that we need to get over the activation barrier just with a little friction. And thankfully we don't have that high of an activation barrier, but still it's high enough to keep it safe. But basically you have this string, and there's going to be our chemicals, our reactants are going to be kind of painted onto this string. And I should mention that they say not to take these apart, so I'm not condoning taking these apart, but I did take one apart a few years ago, and this is what you would see. So you have basically this like what we call Armstrong's mixture. This is going to be kind of like where some of them have Armstrong's mixture. Some of these have like a different form of these, and often these days they actually just have like a spring. But the old school ones or whatever, they're going to have it like this. And then there's going to be paper wrapped around it. And then when you pull the string, you're generating friction that's going to be providing the energy that's needed in order to get over that hump, in order to get over that activation barrier to make this reaction happening. And what this activation barrier is in the case of this reaction is there's a couple things that need to happen in order to get things going. So first of all, you're going to have to break down this potassium chlorate, and you're going to have to break down the phosphorus. We're going to have to break down the potassium chlorate in order to free up the oxygen. So the oxygen in our reaction is going to come from potassium chlorate, but as you can see here, it's going to be in the solid form, and it's going to be tied up with this with the potassium and the chlorine. And so we need to kind of break it off from those. And so we can decompose or basically break up this potassium chlorate into potassium chloride. So basically release that oxygen. This is an example of a decomposition reaction where basically a molecule is coming apart. And whenever you break up molecules, you're going to have to put in a little bit of energy in order to make that happen. So that step would then be endergonic, even if the reaction overall is going to be exergonic. And so we're going to have to add a little bit of energy. We add this energy, we're going to break off the oxygen, and now this oxygen is going to be able to oxidize our phosphorus. But our phosphorus also needs to kind of get activated. So one of the reasons why you need some energy to get this going, and why this isn't just going to randomly catch on fire, because like this white phosphorus is really pyrophoric. So if it sees like oxygen, it can kind of combust. But this red phosphorus is a lot more stable, which makes it better for safe storage. But when we want it to react, we want it to go into this white phosphorus form. How these are different is basically these phosphoruses can kind of, in this red phosphorus form, they're more tied up. They polymerize, they form these kind of like chains of these white phosphorus, which is this, the more reactive form. And so the red phosphorus, it's not going to be like available to react with the oxygen, even if you release that oxygen. But what happens is that when you pull that string, when you provide that energy, you're not only providing energy to decompose the potassium chlorate, you're also providing energy that's going to break up this red phosphorus into this white phosphorus, which is now going to be available to be oxidized. And when it's oxidized, well, now you're getting that combustion reaction that's going to be exergonic. It's going to let off energy. So remember, it's going to let off energy because you have this gain of entropy and because you have that enthalpic gain. And so this is enthalpy, this is referring to heat and stuff. So we're giving off heat because we're going to have a negative enthalpy. So basically, this means that it's going to be exothermic, it's going to release heat. And why this is going to happen is because if we go back and talk about the enthalpy, we're talking about basically the bond strength and the bond happiness. And so if you have more comfy bonds, this is going to be a lower energy, lower enthalpy. And if you have higher high energy bonds, this is going to basically be less happy, less stable, and it's going to have a high enthalpy. So if you go from a high enthalpy to a low enthalpy, well, now you are going to basically, your change in enthalpy is going to be negative. You're going to be giving off heat, and this is going to make this reaction more favorable. So this is going to be exothermic, and then it's going to be combined with the entropic benefit. And why your reactants in this case are going to be, your products in this case are going to be more stable, more happy than the reactants is because when we talk about oxygen-oxygen bonds, so remember we have this like oxygen, this like diatomic oxygen. So oxygen likes to hang out in these pairs, but the bond between the oxygens is fairly weak. And this is because going back to the idea of oxygen being really electronegative, when you have two oxygens bound to one another, they're going to be pulling really, really tightly on one another. And when they're pulling really, really tightly on one another, they're basically both trying to break away from the other one, but they're both pulling back equally strong. And so it's going to be an unstable bond that's going to be easy to break. And so therefore, if you break it, you are going to make it happier and you are going to make a lower energy bond, and then you get that enthalpic benefit. And so this is going to be exothermic because you have that, you're going to be giving off heat. And if you want to know more about this, this is a nice article, why combustions are always exothermic. And from this Journal of Education by Klaus Schmidt-Rohr. So I will post a link to this post if you want to learn more. But basically, our overall reaction is going to be that when we pull that string, we're providing the activation energy that we need. This activation energy is going to be used to decompose the potassium chlorate, to break it down into potassium chloride and oxygen. And then it's also going to, the energy that we provide initially through this friction, and then also by the energy given off by the reaction is going to be used to break down the red phosphorus, this non-reactive form, into the white phosphorus, which is less stable, more reactive, and then it's going to be able to react with this oxygen. When you do that reaction, as we just saw, overall, we're going to get an exothermic and an entropically favorable. So we're going to get this overall reaction that's going to be exergonic. It's going to release energy. So it's going to then use that energy to shoot off the confetti thanks to the bell shape or the whatever the champagne flute shape of the party popper, directing that energy, directing it to be used to shoot out this confetti. And the energy is also going to be used, and the heat is going to be used to help keep this reaction going. So you don't have to keep pulling on the string. The reaction is going to keep going until it runs out of fuel. And so this is going to be pretty fast in these party poppers because there's not much of the fuel on here. There's not much of our reactants on here. But the reaction itself is going to be self-sustaining because you're generating the energy you need to keep breaking down that fuel so that you can use it all up. So I hope that helped you understand the science behind these party poppers, and I hope that you have a happy new year if you are watching this on New Year's, and just a happy year if you're watching this at another time. And so hope that helps you understand, and have fun safely.